Okay.
But sometimes when you're in these really special natural environments, it's like you really shouldn't touch anything
Right.
because you don't want to disturb the natural environment. But in those cases, the icebergs, they're just going to melt.
Yeah,
So it's like,
exactly.
hey, pick up this big thing and do whatever you want with
Did
it
your
because it's
did your
fun.
hotel did your bartender offer to make you a drink with the ice?
Oh no! So we
Yeah.
didn't really stop. I mean, we stopped in, just we were doing the kind of the loop road and just hitting a number of sites per
Yeah.
day.
Yeah. So we brought a chunk of it back like what you had, and yeah, and had it in our drinks.
Yeah, that's super cool.
I know.
And I'm
ten
always,
thousand year old ice in your
amazing.
Coke.
Yeah, I mean
Yeah.
the consistency of it. That's just like that hard pack. It's not like anything you encounter elsewhere.
Yeah,
So
it's a surreal experience to go there. Yeah, the Diamond Beach
absolutely
in Iceland. Hey, so we're
amazing.
live. So who are you? What do you do?
So
Now
my
the
name
question
is
is turned on you, Alex. See how
yeah.
you like it.
My name is Alex Teachey. I'm a postdoctoral fellow at Academia Sinica Institute of Astronomy and Astrophysics here in Taipei, Taiwan. And what I do mostly is look for exoplanets and particularly the moons of exoplanets, which we call exomoons. And I imagine we'll talk a bit more
Yeah,
about
for
that.
sure. So then let's talk about the I guess the state of the art now in searching for exoplanets. How are you doing this today?
I've really just kind of gotten into the exoplanet search for the first time with one of my students. I'm definitely not on the state of the art. We're using pretty tried and true methods, which is in this case going through the test data and particularly looking at this thing called the continuous viewing zone. So, TESS is looking at the entire sky, but there's some overlap at the ecliptic poles where it instead of seeing just a month's worth of the sky, it gets a full year of the sky.
Huh.
And data is, because it's a space telescope, we don't it's kind of data intensive to download absolutely every image. So what they do is they select targets and download that at what we say a very high cadence, meaning a lot of images of those select stars. But then there are lots of images being taken that don't get downloaded every couple of minutes. Those are called the full frame images, but you can still get useful science out of those. And so that's particularly what I've been doing is looking at those full frame images of the test continuous viewing zone in hopes of finding particularly long period planets. That's something that, because I'm so interested in exomoons, we think that the moons are predominantly going to be found at greater distances from their host star. And so, when it comes to exoplanets, I've been particularly interested in these longer period planets.
Getting the same part of the sky, is it like near the pole? Like where is this spot in the sky?
Exactly right. It's at the ecliptic poles. And so the TESS has these 4 cameras that are aligned kind of vertically with respect to the ecliptic plane. And so, they stack up like that. And, the telescope itself stares at one patch of sky for about 27.5 days. And then it moves over to the next patch of sky. And it just keeps kind of sliding along like that. But at the top, there's overlap, right? At the poles, you get these. It's not always the same exact sensor on those stars, but you will observe that star again and again and again. So it's just at the higher latitude you go, the more overlap there is in these fields of view. And so at the ecliptic poles, you get a full year of data, which is quite nice because
Yeah.
again, we're looking for long period planets. They transit much more rarely. And when I say long period planets, these are still planets with probably less than a 1 year orbital period, right? So they would, at least in a system kind of like our solar system, they'd be interior to the Earth's orbit. So they're not super cold, but they're also not, these 10-day orbital periods that we are obviously going to find a lot of those with TESS because of these, these short baselines.
So then what are you hoping to find? I'm assuming I'm sure this is a lot of people are looking in this region as well. It seems like a pretty juicy spot to search for planets.
Yeah, right.
What have you found in there so far?
Well,
or what are
this
people
is an
finding?
ongoing project. Yeah, this is sort of my first chance to work with a student, which has been really exciting. I've got a really fabulous student, and he's applying for graduate school now. So I'm hopeful that he will land someplace great. So it's been sort of exploratory for me to do the planet search for the first time, and obviously for him, it's mostly his project. And so we've been using, pretty tried and true methods, looking for these transit signals, and then once you find potential signals, then you go and fit them and see if they are actually planets, or maybe they're eclipsing binaries or something like that. So it's ongoing. I would say that I'm not doing anything really revolutionary when it comes to this, but yeah, we'll see what we find. There's a lot of data to go through. Obviously, a lot of people working on it, but you never know if you hopefully find something novel in there.
And we've talked to people searching for exoplanets plenty in the past using the transit method, the radial velocity method, etc. Your specialty is in exomoons.
Right.
Why are exomoons important?
It's a great question, and I answer it in every talk that I ever give. There's really a variety of so hopefully it's well rehearsed. There's really a variety of answers to that question, I think, but where I would always start is to say that when we're doing exoplanet work, and by extension exomoon searches, we're of course learning a lot of amazing things about these worlds. They're fascinating in their own right. But we're also turning a mirror on ourselves, right? Every time we learn more about these other places, we learn more about ourselves. In what ways are we ordinary, and in what ways are we extraordinary? And I think that's still very much an open question, and bears directly on this question that I think is really fundamental, which is the search for life. How common are we? Are there lots of other folks out there to talk to, or are we spectacularly alone? It's an open question. And so when we see our own solar system, we had a very tidy picture of how it came to be. We see a lot of moons, particularly in the outer solar system. It's a good guess that we will see a lot of moons out there in other systems, but until we see them, we really don't know. I mean, that's just sort of one piece of the puzzle about understanding, who we are, what is our context in the Milky Way galaxy. Apart from that, what I would tell astronomers is that we think that the moons can be important tracers of a dynamical history, meaning, how did these systems form and evolve? If you look again at the moons in our solar system, they provide a lot of clues as to what was happening in the early formation. Whether you're looking at Earth's moon, we've got a large moon that seems to have been caused by an impact. Mars got these two little small moons. Jupiter's got, huge number of moons. Saturn, Uranus, they're all tipped up on the side, just like the planet is. Neptune's got this captured moon. Pluto, all these Kuiper belts, all of these moons, they're all providing important clues as to what was happening in the early years. And again, when we're looking at these exoplanetary systems, we likewise see just a snapshot in time. We're able to see these protoplanetary systems. And then we see other systems that are billions of years old. We just get that one shot at it. And so we need ways of figuring out what happened in the past to these systems. And finally, I would say that, if you look at the moons in our solar system, they are attractive places to look for life. They are geologically active and diverse. They have an abundance of water, in some cases liquid water, we think, and in at least one case in our solar system, a thick atmosphere.
Right.
And so when you think about the moons in our outside of our solar system, similarly, they could be attractive places to look for life. And, in the next few decades, I think these places, just like the rocky planets that astronomers are so interested in characterizing in the coming decades, these moons, I think, are just as fascinating and interesting worlds, real true worlds in their own right. And so I think they will be deserving of not just discovery, but characterization in the decades to come.
So, we're familiar with the moons that are here. Sorry, I'm reconfiguring the video a bit here. My computer was complaining about the amount of resources that I have, so I'm having to muck around with it a bit, live in real time. So apologies in advance, but in our solar system, we've got the moon. We've got the moons of the gas giants, as you said, which are fascinating worlds, ice
Right.
worlds, potentially with liquid water underneath. You've got Titan, which is just a weird moon with, as you say, a thick atmosphere. There are reasons to think why the moon of Earth is essential for life on Earth. There's reasons to think that these other moons could have life underneath them. And so, the trap that we fell into last time is that as we look around the Milky Way, we're going to find planets like the solar system. We're going to find some terrestrial planets. We're going to find some gas giants. We're going to find some ice giants. We're going to find some dwarf planets, etc. And yet the reality turned out to be wackier and crazier than we ever could have imagined. So what are, I guess, exomoons that you can imagine that we have no analog for here in the solar system?
Yeah, it's a great question. And I think, easy place to start is this candidate moon that we, potentially identified a few years back around this planet Kepler 1625b. Say candidate because, today it's not a confirmed moon. Sometimes people talk about it as a confirmed moon. Some people say, it's entirely not there. Our expert opinion is that it is maybe there, but it is unproved. And anyway, the interesting thing about this moon, if it's real, is that it is spectacularly large, much larger than anything in our solar system, the size of Neptune. And that by itself is reason enough to be skeptical, but you can't write it off entirely as just totally implausible. So this moon, if it exists, size of Neptune, the host planet is a few times more massive than Jupiter. If you do the math there, the mass ratio between these two moons is only about 1%, which is actually the mass ratio between Earth and our moon. So even though we're really not used to the idea of people say, well, that looks like a binary planet, and how can you possibly have something the size of Neptune going around a super Jupiter? But it's plausible, and there were papers that came out in the wake of our work saying, yeah, actually, you could make this through some sort of capture scenario. So that's just one example of something that you might have. In fiction, we see moons that are Earth-like, right? That is Indor and Pandora.
How would that work then?
Well, you would obviously probably want to be a little more massive, which is, again, totally conceivable. So, you imagine a moon orbiting probably a gas giant. The moon itself is, closer to an Earth mass rather than a moon mass. We're talking 10 to the 24 kilograms or so. So it's able to hold a thick atmosphere, maybe even has its own magnetosphere or something like that. But it's quite interesting that, people have done work about how you could have something like this. For example, there is what they, basically like a moon habitable zone, just like we have a habitable zone around a star based on how much light you're receiving from the star. You also get internal energy from orbiting the planet, right? So, Jupiter is a classic example where we see Io is this volcanic world. There's just tons of energy in there. And then, as you go farther out, obviously there's less energy being injected in there. That's an important part of the energy economy of a planet. So you can kind of do that math again and say what sort of range of orbits around a planet might give you an appropriate energy economy to have, say, stable liquid water on the surface and that sort of thing.
So you could have, you could have a planet that is orbiting a star, and it's maybe just outside the habitable zone of that star, but then the planet has a moon, and through tidal interactions, it's warming up the moon. So suddenly, when you get the sunlight plus the tidal heating, you're back in the habitable zone.
Right, exactly. Now, there's all kinds of other, considerations. Moons, we tend to see them as tidally locked, right? So, that's going to be something very different than the Earth, where, you're going around and you have several days, more like our moon, where you have several days soaked in darkness and then several days of, unending sunlight, starshine. So, these are very much open questions, and, it remains to be seen whether you really truly can have something kind of like an Earth analog as a moon. At the very least, I think life would be quite different, but, still potentially habitable, I would say. And this is why we have to actually find them. This is another sort of important thing. We have this ongoing dialogue between the theorists and the observers. We have this all throughout astronomy. And when it comes to these sorts of things, moons in particular, the theorists can get way out ahead of us. They've had, decades to study the moons in our solar system. Again, they have a very tidy picture about how these things form. But we really need to test all of these ideas in an exoplanetary context to really know whether these things are possible or plausible or maybe even abundant. These are all very much open questions.
It does feel, I mean, as you say, it feels like it's inevitable. It's a no-brainer that these things are out there. And yet, so far, your team has one candidate object. I've heard rumors of others in the past, also from your team, I think, or from David. David Kipping, the head of I guess your advisor back in back at Columbia. Right. What is the technique? How much more difficult is it to find an exomoon than to find an exoplanet?
Well, it's a lot more difficult. Otherwise, we would have found more of them by now. I think, there's a combination of observational features, both from the instrumentation side and also just sort of geometrical or temporal facts of life that we are contending with. So let me talk about those briefly. A moon, of course, is much smaller than a planet generally. I mean, you can maybe imagine a moon that's the size of the Earth, but we have no solar system analogs for something like that. So if we're just looking for solar system moons, they're quite small and really at the very low end of anything that we have been able to detect by transits. Now, I think it's still very important that we look for the transits because, again, we might very much be surprised by what we find out there. You should never exclude the possibility that you'll find something much larger than a solar system analog. But, if that's our frame of reference, then these things are already quite difficult to detect. And then, we're contending with this issue of if we're looking for transits, imagine a Jupiter analog. A true Jupiter analog orbits at something like 5 astronomical units, takes 12 years to go around. Right. The nominal mission of Kepler was 4.5 years, right? It was supposed to be longer, but we got 4.5 years staring at those stars. So just from a time standpoint, you have a 1 in 3 chance of seeing a single transit of a true Jupiter analog, right? That's setting aside the geometrical considerations, which say that a longer period planet has a much lower probability of transiting just by getting the angle just right. The farther out you are, the more perfectly edge on you have to be. So we're continuing with that as well. So, maybe it's not surprising that we haven't found these moons yet. I think really the question that we were not maybe fully contending with before was that we were asking the question whether or not you can have a lot of moons at small distances from the star, right? We kept saying we're just looking for moons, just like we're looking for moons in our solar system. But what we were really doing was looking for moons close into the star. And we don't see any moons. Mercury has no moons. Venus has no moons. Could they have moons, right? Earth just has this one large moon, but we don't know how anomalous that is.
And then Mars has tiny moons.
These tiny little ones. Yeah. So when we think about the big moons, they're mostly in the outer solar system. But, again, we have been surprised with our exoplanetary discoveries, right? Because we have found these Jupiter mass planets at distances from their star that is so much smaller than anything that we have an equivalent for in the solar system. So it was a very important question to try to answer. And I think we have gotten kind of an answer to that. It's maybe not the answer that we wanted, but it's an important answer.
So then, like going back to say 55 peg, It's a 51 peg. Yeah.
51 peg.
Yeah. So, you've got this giant hot Jupiter orbiting around its star. It's only taking a few days to make an orbit around. If it had a large moon, a Neptune-sized moon, I guess it was discovered with the radial velocity method. But imagine a hot Jupiter that was discovered with the transit method with a giant Neptune-sized moon, and it was orbiting really close into the star. What I'm getting from you is that should be a thing that is detectable.
Well, that would definitely be detectable, and I think we can probably, strongly rule that out on observational grounds and really on theoretical grounds as well.
And
when you get to the star, what we call the Hill sphere, the sort of the gravitational influence of the planet is so small. There's two limits when we talk about moons. There's an interior limit. You get too close to the planet, you get torn apart. You get too far from the planet, and you get stripped away. Right, that region shrinks so small when you're talking about hot Jupiters that you could never really have I'd have to do the math. I feel pretty confident to say you could never have a Neptune-sized moon. You could potentially have something like an Io, a really small little moon, really hugging the planet. And actually, folks have been looking for these through actually spectroscopic signatures. And so, this is another interesting question that we can try to answer. But I think it's safe to say we would never find a Neptune-sized moon around a planet like that anyway.
And so that search that you did, that's really interesting because you're essentially saying, should Venus have had a moon? Should Mercury have had a moon? Could Earth have had 17 moons? Could Mars have had bigger moons? That is the lack of moons in the inner solar system a solar system thing, or is it a limits of astronomy that if your planet is orbiting too close to your star, the star eats your moons, and that's that. And so, have you been able to get that answer? Have you been able to provide those constraints to some degree to say, here's where we're pretty sure moons don't exist?
Yeah, so that was actually my first paper with David Kipping when I started as a graduate student. We were looking at kind of the population. We had this pretty nice technique that we had gotten from another Exomoon researcher, Renee Heller. The idea is that, if you have consider a single planet around with a single moon, and it's going around the planet, of course, every time it transits, the moon shows up in a different place. So you lose a little bit of starlight, sometimes over here, before the transit or after the transit. But if you take a lot of those transits and stack them on top of each other and take a time averaged signal, what you will see is sort of a drop in the starlight, the flux, we would say, on either side of this planet. And it turns out that you can do the same sort of trick with many planets, right? So each individual moon might be very challenging to detect, but you could take a lot of planet transits. And in that work, we took several thousand transits and stacked them on top of each other and looked for this missing flux due to the presence of a population of moons, not a single one, but many moons out there. And what that allows you to do is actually shrink the uncertainties down enough that you can start making some meaningful statements about the occurrence rate of these moons. Now, there is a sort of what we would call a degeneracy there, where you have two variables that are playing off one another and you can't really tell which one is controlling it. The degeneracy here is the occurrence rate of moons and also the size of the moons, right? So you can lose a lot of flux because you have big moons or because you have a lot of moons and you don't really know which one is which. So you can kind of ask that question and run the numbers and place some, for the first time, meaningful constraints on the occurrence rate. And we find a low occurrence rate. It's you have to kind of set one parameter and do the other. So what we can say is an occurrence rate of Galilean analogs, meaning like the big moons of Jupiter. How frequently do we see something like that in the Kepler data? And the answer is something like 0.16 plus or minus 0.13.
Right, but you're still, which is a low number.
Low, yeah. It's low.
But right. That's still in this case having planets that are relatively close to the star. So be Galilean moons around a Jupiter that is orbiting within the orbit of Mercury.
Exactly right. Yeah, much closer in. So true Jupiter analogs We have a couple of examples where we can call something a Jupiter analog because it has a similar level of insolation or installation, receiving the equivalent amount of starlight that Jupiter is. There's this planet Kepler 167e, which is only at about 2 AU or something like that, but it takes several years to go around and receives the equivalent amount of starlight. We would say that's kind of like a Jupiter, but a true Jupiter way out five astronomical units. We really don't have many examples of those in the transit data. When it comes to radial velocities or these other detection methods that we have found some of those planets, but with transits, those are pretty hard to come by. So
what, I guess, if money was no object and you had the best telescopes in the world at your disposal, what if you were to design a mission that is purposely looking for exomoons, would it be any different than a amazing just exoplanet hunter?
Well, yeah, I think there would be a lot of similarities there. Aperture, the size of our mirror really is everything when it comes to the time domain science, right? You can imagine taking a telescope and if you're looking at a fixed object, say you're looking at a very distant galaxy or something where it's not changing at all, at least in an appreciable time scale, you can just take all the light in that you want. You just keep drinking in the photons.
Right.
And you can see these very, very faint objects, even with a modest telescope, right? A mirror really does two things for you. It soaks up a bunch of light, and also the larger the mirror, you get a better, angular resolution, right? In a case of looking at transits, we don't really need angular resolution because we're just monitoring the brightness of essentially a point source. But because we're now in the time domain, you can only soak up a certain amount of photons per unit time, right? Just like my eyes can only see so much when I'm staring at the sky, but then I take a long exposure photo, and then the Milky Way just pops out, right?
Like during the transit, you need as many photons as possible.
Exactly right. And the baseline, just to shrink your error bars down, you just need a bigger mirror. So if we had a bigger mirror, we would be much more sensitive to these small transits, and that would be fabulous. Also, we just need really long time baselines, right? So we really need to be monitoring. Kepler was fabulous, but monitored one patch of sky. TESS monitors the whole sky, but just gets these very short baselines. So if we could really have the best of both worlds, monitoring the whole sky for very long baselines, I think that would be a huge amount of data. But I think we really would start to detect these things. One thing that I sort of tell people about the exomoon search is that it's in some ways fundamentally different from the exoplanet search, because we got very spoiled with these short period planets. Again, it was no guarantee that they would really be there, and they just kind of fell into our lap. These hot Jupiters we now know are not super common, something like 1%.
Right.
They're not incredibly common, but there's enough of them, and they're easy enough to see that we get to study them. They come around every couple of days. If you want to observe one with Hubble, you say, oh, we'll just point it there on Tuesday, or we'll point it there on Friday or the following Wednesday, and you can get your data, right? When it comes to looking for these long period planets, we have to, we get far fewer opportunities to observe their transits anyway. And, if you're thinking about radial velocities or any kind of method that you want to use to observe these, the time baselines to observe these events is much longer. Fortunately, it's not so bad as if your whole career was built around observing transits of Venus, you'd be in trouble, right? Because we only get those once every 110 years or something like that. So it's not that bad. But, we do have to get sort of comfortable with the idea that sometimes we'll make an observation and then we don't get to see that planet come around again for another 3 or 4 years and transit again. And, if we had enough of these systems, then we could, really make it a kind of regular thing. We're going to observe this one. We have a whole calendar of the ones that we're going to observe. We don't have to just twiddle our thumbs for 4 years waiting for the next planet to come around. But we need to be laying those foundations in order to get the observations that we really need. That's why I'm sort of really excited about this global effort with with the unistellar group, this citizen science where I think they just did it actually, performed an observation of this planet that I mentioned a few minutes ago, Kepler 167e, this very long period planet, and they've enlisted the global community to observe this transit because it is really a special event. We don't get very many of these, and observing from the ground, obviously you can be clouded out. You have to propose to get this telescope time. You got to make sure that you actually get the telescope time, it doesn't break down, and you've got clear skies. So really going to space is the only way that you can guarantee that you'll be able to see these events unobstructed. But yeah, we have to lay the groundwork and play the long game a little bit.
So, you're mainly talking about the transit method. I mean, there are other techniques to search for planets, the radial velocity method, direct imaging, and even some astrometry. There's some even more interesting and extreme methods that are starting to pop up, like detecting the magnetosphere of a planet because of the radio emissions. Again, do any of the other methods seem intriguing to you as a way to search for exomoons?
Yes. So, I've just been talking about the challenges of transits. And so I think it is very important that we, explore other ways of looking for these things. And fortunately, I do think that in the coming years, we have some exciting possibilities. For one, there is, increasingly the possibility that we will be able to measure the radial velocity of the planet, not the radial velocity of the star, but the planet itself. So we see the planet through direct imaging, right? In these cases where we have something beta pick, where you see the star, but then you can see the planet resolved separately. If you can get the spectrum of that planet, then all of a sudden you can measure reflex motion of that planet and potentially detect moons that way. And so that was proposed a couple of years ago. And just in the last few weeks, they put out a first paper where they tried to do this. The data was not meant for this, and they put, sort of upper limits or lower limits on these masses that are crazy high. They say, okay, well, we're sensitive to a moon that is twice the mass of Jupiter or something like that. So it's not great right now, but it's a proof of concept. I mean, really, in the coming years, we should be able to do
really
that as our spectroscopic methods become more sensitive. So that's really exciting.
So before you move on, then I want to kind of dig into this a little deeper here. So so you're with the radial velocity method, you are measuring the redshift of the light coming from the star and using that to infer that there's a planet orbiting around it. And so with direct imaging, you're now taking it one step farther. You are imaging the planet and then watching the spectrum of the light coming from the planet and using that to infer the existence of a moon going around that planet. That seems really feasible.
It's feasible. It's very hard.
I'm assuming you've got a telescope capable of direct imaging planets.
Right. Yes. So, one big challenge with this is that this is really only appropriate for a handful of nearby planets. The direct imaging planets that we have, even though direct imaging has been around at this point for, 20 years or more, the best we can do is see these planets that are at wide separations that are also nearby. You can imagine, the closer a system is, the more they are separated on the sky. And as they get farther away, they're closer together. So our angular resolution only allows us to observe these quite nearby systems, and the planets tend to be shining by their own light. They tend to be very young systems because we're really seeing their heat from formation rather than their reflected starlight. In time, we should be able to get closer into the star, right? The star is billions of times brighter than the planet. So that's part of the reason why we have to go so far out is, the star is just overwhelming us and we have to block out that light. In time, what they call the inner working angle, how close we can get to the star, that is expected to shrink. And then also, our spectroscopic measurements should be able to get better in time for measuring these planets. But these planets, they are, a little more complicated than stars. Sometimes they have all kinds of stuff going on. You would now kind of be looking at the stellar spectrum as well as the planet's spectrum and trying to disentangle those. The theoretical work has been done a couple of years ago, or at least some of it, Important Foundations by Andrew Vanderberg. It seems feasible, but it, like any other technique, is going to have its limits. So it's not gonna solve all of our problems.
Right.
But I think in the next 10 years or so, we really could have some exciting detections with this method.
And it sounds like actually the transit method comes back on the table again, because now if you are able to image the planet for long periods of time, you could detect changes in the planet's brightness as the moon is passing in front.
Potentially, you'd have to have the geometry would have to be just right. We're always dealing with this, chances are, I mean, it's much better chance that you're going to see something a little tipped up. But of course, that's what's nice about the radial velocities, is that you can see them even when they're not perfectly aligned. Right? There's, again, sort of a degeneracy here between the inclination angle and the masses of these planets. That comes into consideration. But direct imaging, as we get better with LUVOIR, or the infrared and optical and UV large telescope that shall not be named based on the Decadal Survey. This is really exciting. And of course, we can do that work with ground-based telescopes. Most of that work has been done with ground-based telescopes, with these extremely large telescopes and adaptive optics. And these spectrographs that are enormous. Like I say, 10 years, I don't know exactly what the timeline is, 10 to 20 years. I think we should have some of these detections.
One of the other ideas that sort of popped up to become more popular recently is this idea of rogue planets, that there could be as many rogue planets as there are regular planets that either formed in situ out of smaller gas clouds or debris clouds, or planets that were kicked out of other star systems are now freely roaming the galaxy. And in theory, these planets could have moons. Yes. And now you don't have the brightness of the star to contend with if you can detect the planet in using some very sensitive infrared observatory or something. Does that give you a better shot of being able to detect moons?
Yeah, so I think this is
or brown dwarfs, right?
Right. So this was another paper that just recently came out, where they said, okay, let's look at the brown dwarfs and look for transits of the brown dwarfs. Right. If you imagine a brown dwarf, something like Jupiter, right? They are roughly the same size, and of course they are shining by their own light. They're very cool, but we still see them in the infrared, right? So they are emitting light themselves. You can look for these transits, and these transits, if they are true moons, if they've been formed like a moon, they'll be pretty close in, and so you have a pretty good geometric probability of seeing them, as well as a temporal. You've got a good chance of seeing these transits. It begs the question: is that a planet and a moon, or is it a brown dwarf and a planet? Does it really matter?
Right.
I have sort of watched terminology discussions in the community with some mild irritation, because ultimately it doesn't really matter. Right. What we call them, except for how you sell your science sometimes, right? So exomoon stuff gets a lot of attention, and so sometimes I guess I will be a little sort of wary of people calling things moons if it's really just a planet. But again, the dividing line between those, when it comes down to it, is not clear at all. We're talking about formation mechanisms, right? How did this thing come to be? We're interested in that question. I really want to know, if I see something like a brown dwarf that has something orbiting around it, did it form as a in a circumplanetary disk, and that object was originally a planet that got kicked out? And how did that happen dynamically? How did the moon survive? Those are all a variety of interesting questions that we would want to interrogate. And ultimately, what we call them is less relevant. But you can certainly call them a moon, because they would otherwise have the hallmarks of one.
Now, earlier on, you talked about the importance of moons and its relation to the search for life out there in the universe.
Yep.
What is your instinct right now about what role moons are going to play in the formation of life in the universe? Some people say that that Earth needed a moon. We wouldn't have life on Earth to the extent that we have without the moon. Others are not so sure. So what role do you think moons play in life?
Well, I will confess that I am not. I would say that I'm not well enough educated on the moon as essential for life on Earth debate to really take a stance on it. I've heard those arguments. I guess I kind of land in the life finds a way
Yeah.
in a category. So, would life look different on Earth without a moon? Certainly. I mean, we wouldn't have these life cycles with the sea turtles following the moonlight. And you think of countless examples where the moon has played an important role in what happens here on Earth, and those obviously go out the window if you don't have a moon. Does it protect us from impactors, or does it throw impactors our way? Things would certainly be different without a moon. But to say that you have to have it, I'm a little skeptical of that. Just on the surface.
Yeah, I think that's exactly. I love that. Right, life finds a way. That it's funny. Like people, and this is way out of your wheelhouse now. But people say, well, maybe single cellular life is common, but multicellular life is far less common, and that's why we don't see life everywhere. But even that, like, I can imagine single-celled life forms forming into colonies that are behaving like multicellular organisms, like give life time and see, who knows what it'll be able to come up with.
Certainly, yeah.
But then when we look at, for example, these icy moons, places like the ones that are orbiting around Jupiter, Saturn, perhaps Pluto, Charon, it just goes sad. No, I mean, this goes on and on and on. There could be by a factor of 1,000 more of these icy worlds out there than there are habitable terrestrial planets. It actually shifts the diversity of life into these kinds of worlds.
Right.
And yet they're really tough to study, because the life you're going to be finding is under kilometers of ice. So
exactly right. Yes. So one thing that's sort of amazing about astronomy is how much we interface with a variety of other fields. And one thing that fascinates me is the question of abiogenesis. How do you get life to start? And I think that's a sort of fundamental question to life on these moons. We have sea life deep underwater. In the most extreme environments here on Earth, we see life. You have these black smokers on the bottom of the ocean. It's otherwise kind of a desert down there, but then you have these oases on the bottom of the oceans, kilometers underwater, extremely cold, very hostile environments, and yet life thrives down there. And so, it's totally imaginable that you could have something like that on Europa or Enceladus, say. The question is whether you can start life that way, or whether life colonized those environments, but really needed something more like proper solar radiation in order to get going in the first place. That's very much an open question, right? So when it comes to moons, maybe you could pluck something from the bottom of Earth's oceans and drop it into Europa, and it would do just fine. But could you get something there in the first place? And then there is this question that you have raised about studying them. Obviously, we've got plans to do in situ exploration of these icy moons in our solar system, and I can't wait for that to happen. I mean, I'll probably be dead by the time we're actually doing it. Or landing
goes in, yeah.
But that's super exciting, and who knows what we will find. Just like Mars. I mean, Mars is a place where we think, you could have life. I mean, I think people generally agree that life could be there, and yet we haven't found it yet. And so, even if life is similarly on these moons, it could be spectacularly difficult to find. It could be, sitting many kilometers underneath the water, and we drill down on the surface and we'll take a peek around and say, wait, I'm not seeing anything. So that could be the case. When it comes to these exoplanetary systems, the moons are going to be a challenge, because, at least in the near term, what we're thinking about is atmospheric characterization, right? So we can actually look at these right now anyway, these gas giants. The plan, of course, is eventually to be able to look at terrestrial planets, look through their atmospheres and see the constituent molecules of those atmospheres. If you just have a icy rock, there's nothing to look through, right? I attended a sort of interdisciplinary conference several years ago that was about astrobiology, and you had exoplanet people there, and you had planetary scientists, geologists, and all about the search for life. And when the geologists came in, they started talking about how you could detect life, underneath the surface, and all the exoplanet people were being like, "Well, what else have you got for me? Because that's not going to work. We're not going to." We can't drill down into the surfaces of these exoplanets or exomoons. I guess I have a little bit of faith in astronomers and scientists more generally. We are always seeing these amazing ideas come out of people's brains.
Yes.
And the things that I have not imagined today is, we could do all kinds of amazing things that nobody has thought of yet. And I think that's one of the sort of the thrilling things about this business is just that, people have a new idea, and 5 years from now, 10 years from now, it's a revolution. And now we have this new technique to look for these things. Sometimes I'm an optimist, sometimes I'm a pessimist. I'm sitting here saying we've run out of things to try, but we never run out of things to try. New people come along with fresh ideas, and we'll get some amazing stuff out of it. And I can't foresee it yet, but I think it will happen.
Well, so you mentioned this earlier, just this balance between the theorists and the experimentalists. So you're would you consider yourself in the experimentalist camp, the observer camp?
Mostly. I mean, I have been sort of dipping my toe into theory, but more from an observational perspective.
Right. Yeah. So
trying to dream up new ways of looking for these exomoons. Yeah.
Yeah.
But not formation type stuff. Yeah.
And so how do you feel about that balance between, we see it run amok in the particle physics world, where you've got people taking, say, string theory to the nth degree, and on the other hand, you've got the people running the Large Hadron Collider and trying to desperately find things that are an infinitely larger mass than the strings. Like, we would need to have a particle accelerator the size of the solar system to find the strings that the theorists are working on. And so the theorists kind of always get ahead of the experimenters. And yet the experimenters sometimes discover things that the theorists never thought of. So there's this really interesting dichotomy. How do you sort of feel about the balance as someone who's in definitely one of those camps?
Right. So I think maybe I mentioned it before, but so much of the moon study has been sort of predicated on our understanding of our solar system, and that makes a lot of sense because you do the math and you run the simulations and you say, okay, well, this pretty much accords with what we expect. So I think we're doing a good job, right? It's a lot harder to check yourself against reality when you are pushing out into the unknown. You can make all kinds of predictions, but then it's not, you don't have anything to test it against until we've gotten out there. As an observer, I would say that I tend to take what the theorists are saying seriously, but I'm not going to let that restrict me to saying, well, it can be this way and it can't be this way. So the theorists, there's sort of a big canonical result at this point says, well, when you make moons out of a circumplanetary disk, this is due largely to Robin Canup, who's done a lot of important work on the formation of moons. If you're making a system kind of like Jupiter's moon system, the Galilean moon system, they say, well, you can't really make anything larger than 10 to the minus 4 mass ratio, a 1 to 10,000 mass ratio for the total satellite mass. And that accords with what we see for Jupiter. And, that seems reasonable. And, they have solid foundations for believing that. Nevertheless, I would still look for something larger.
Yeah.
Maybe it's there, and maybe we need to go back to the drawing board a little bit. I take it seriously, but I'm not going to let that hold me back from postulating that there might be something that hasn't been imagined yet.
That's interesting. So, and then of course, if you do come one that is, I mean, that's the dream, right? That you get to drop in the lap of the theorists, one that completely shatters their expectations for what they had been imagining, and now they're scrambling to incorporate the true observations, because the observations are like the truth, and is what nature is trying to tell us. And that's
right. Yeah. So this was a sort of important component of the Kepler 1625 finding, or potential finding. Because it was not a solid detection, and I think we were the first to admit, it was a candidate, but it was not a sure thing. I was sort of uncomfortable with the idea that people were already writing theory papers about how you make it.
Right.
And then there were a few of those because I said, well, maybe you guys are chasing a phantom, and I felt that way. I felt a little uncomfortable about it. Nevertheless, it was still very important because it did give some sort of theoretical backing to the idea that this thing could exist in theory. And I think it was valuable because even if this particular object doesn't exist, it at least shows that maybe something like that could exist out there. And therefore, it's worthwhile to look for more such objects. So, it was sort of gratifying to see, people sort of scratching their heads and saying, well, how would you make something like this?
Yeah.
And like I mentioned before, reason enough to be skeptical that something like it could exist at all. But yeah, if you can find something that's unexplained, not sort of defies easy explanation, that's super exciting for us.
How do you feel as an astronomer at the results of the Decadal Survey, the new wish list? Have you read the survey? Have you, or at least seen summaries of it?
I looked over it. I didn't pay it terribly much attention.
It's a big document.
Yeah. It's huge, and remains to be seen how much of it will actually come to fruition. It's a big wish list. I understand that it plays a powerful role in sort of laying out where we're going to go from here. I guess when it comes to exomoons in particular, I don't know if it's defeatist attitude or what. I've just kind of reconciled myself to the fact that in the near term, we're not going to have a huge buy-in from other astronomers. Everybody's got their own thing. Everybody's, doing what they want to do. Yeah. And I sort of proselytize for exomoons. Whenever I give a talk, I say, I'd really love more people to get into this, because then we get more brains chewing on the problem, and money and funding and resources follow where the astronomers are. If we had more exomoon people, we'd have more exomoon resources. But I in the near term anyway, I think there's just not going to be that much buy-in. I don't know. It's because people are just a little too pessimistic about the prospect of finding these worlds. I don't know what it is, but in the near term, what that means is that I need to work within the confines of what the astronomy community more broadly is providing. So, we are thinking about what you can do with JWST, for example. We're not thinking, at least I'm not thinking about, what kind of exomoon telescope would I build? I just don't see myself as the next Baruchi or George Rickert, leading some massive telescope operation. I just take what they give us and try to work with that. And there's a huge amount of data, right? I mean, Kepler and TESS and these survey telescopes, Gaia is amazing, LSST, or Vera Rubin coming down the pike. I'm so excited by the sort of the huge initiatives that we can just kind of piggyback on all of those.
It's funny. Like, I don't think anybody has a problem with the research, and nobody, I'm sure, thinks that you're not going to find them. It's just it's too hard.
It's hard. Yeah.
It's hard. It's super hard. Yeah. And so I guess it's sort of people saying if you can do it, then do it. But if you can't, have you thought about gravitational waves? Have you considered, other fields? Do people do some interesting work in, solar flares these days?
Exactly. People are doing, I think it's important for me to diversify. But at the same time, when I was applying for postdocs, I said, well, I could go and do something a little more quote unquote conventional. But there's a lot of people that are already doing that and doing it better than me. Right. I mean, I could get into atmospheres, but how many, 100 other astronomers are doing atmospheres right now? There's very few people doing exomoons. And so not to put too high a value on my own contributions, but I did kind of feel like this is a, special skill set that I have been developing over the past several years. And it's something that the community should have. We shouldn't have fewer exomoon people. We should have more. Yeah. So if I retreat and say, okay, I'm going to go and work on something that everybody else is more interested in, then that's a loss for exomoon science. And ultimately, as much as I like doing this work, I'm really just more interested in seeing breakthroughs with exomoon science. So I'm just going to kind of stick to my guns, and hopefully somebody will pay me. I'm fortunate right now. Someone wants to pay me to do this work.
Yeah.
And who knows how long that'll last, but for now, I'm pushing ahead with it.
Yeah, absolutely. Well, Alex, it's been super fun to talk with you. If people want to follow your work, where should they go? Where can they find out more about you?
I'm most active on Twitter. It's just my name @AlexTeachey. I also have a website, alexteachey.com. You can find a little bit more about my work. But follow me on Twitter, I guess.
And you're a regular contributor on the weekly Space Hangout. So
that's
talking about, testing out, sampling other fields of astronomy, trying them on, see how they feel.
Yeah, definitely check us out on the weekly Space Hangout, as always.
Awesome. Well, Alex, thank you. It was a pleasure to chat with you. I'm really excited for the work that you're doing. I think it is really important, and I'm glad you're doing it. And I look forward to hearing your first concrete, no question announcement of an exoplanet. Ideally, Endor. Like, it's just going to be Endor. As soon as you find it, then you're going to be then you'll be the toast of the town.
Well, thanks, Fraser. It's been a great chatting with you. And
all right, thanks, man.
Thanks for having me. Yeah.
All right, take care.
Take care.
Stop stream.